All right, so we have verified two of these boundary conditions, and those weren't too bad. Those kind of appeared right away. And now we have two more that we need to verify to finalize this solution, and then we can be confident in our concentration profiles here, and we can start answering that question of can we match what we found out with the resistance network. So let's see, we have two to choose from. Neither one is going to be very, very easy. I think let's start with matching the fluxes. So what we need to do is take the first derivative of each of these functions and then multiply by the diffusion coefficients, and then we'll be able to see if this is true. So let's start with this Pyrex. If we take the derivative with respect to y, we get nothing for the initial concentration, and we just have the second function here. So looks like y, everything else here is a constant, and y multiplies this constant. So the derivative of this with respect to y, let's write down. Is just going to be, I guess, let's bring the concentration here. So we have concentration naught over yi. So we're looking at the derivative of the concentration profile in the Pyrex is naught over yi times d, the diffusion coefficient ratio. The diffusion coefficient through the silicon dioxide over the diffusion coefficient through the Pyrex, all over this denominator. 1 minus h over yi minus this diffusion coefficient ratio. All right, that wasn't too bad. And so let's take a look at the derivative in the, on the camera here, SiO2. We have, first thing we can do is split up this, right? We can write this as y over yi minus h over yi. And if we distribute over here, then we'll have, well, the entire portion that's the negative h over yi times this, there's no function of y there. There's no y dependency. And so we really will focus on the first half here. Y over yi times this. Again, if we take the derivative with respect to y multiplies everything else. So what we need to do is take yi, actually, yeah, we could write that as, again, CaO over yi, then over this denominator. So I hope that's not too much to follow along with, but we'll have the derivative of A with respect to y in the silicon dioxide equals Ca naught over yi over this denominator. All right, and the boundary condition we were trying to satisfy says this. It says we have this ratio of diffusion coefficients. Actually, it's here, so let's rewrite this as DAS over DAP. We can let the negatives cancel. Equals, so we have this diffusion coefficient over this diffusion coefficient will then equal dCA, the differential change in the concentration of A through the Pyrex over the change in the silicon dioxide. So we'll have this over this. This should equal C naught over yi. Actually, I don't need to really, let's just put a big division symbol here, and we can see that C naught over yi is going to cancel, this denominator is going to cancel, and sure enough, we're going to have this diffusion coefficient ratio is the only thing that's left if we take that ratio. Okay. All right, so a third check, and finally, we need to check that the concentrations at the interface are going to be equal.